Hello. Today, we're going to tackle a fascinating problem involving an integral equation. By the end of this video, you will be able to solve an integral equation by simplifying the integral, using a key integration technique. Our goal is to solve the equation you see on the screen for x, where we are given that x must be a positive number. Looking at this equation, the most complicated part is the definite integral. Our first step will be to simplify this integral as much as possible. Let's call this integral I for simplicity. So, we'll focus on evaluating I, which is the integral from e to x of t, raised to the log of t, multiplied by the quantity 1 plus 2 times the log of t, all with respect to t. Our objective in this scene is to break down the integral I using algebraic properties, which will prepare us for integration by parts. We start with our integral I. The integrand, which is the function we are integrating, is t times 2 log t. Let's distribute t times 2 across the parentheses. This gives us the integral of t time log t plus 2 times log t times t time log t, all with respect to t. Because of the properties of integrals, we can split this into the sum of two separate integrals. This is a crucial step that simplifies our problem. So I becomes the integral of t times log t plus the integral of 2 times log t times log t. This decomposition into two integrals is a standard tactic. By separating them, we make the problem more manageable. Now, observe the second integral. The 2 log t term can be expressed as a product with 1 over t by introducing a factor of t. Why would we do this? It's to put the expression into a form that's ideal for integration by parts. We want to see a function and its derivative. So, to recap, we've taken our original integral and broken it into two parts, then algebraically rearranged the second part. This setup is perfect for the technique we'll use next. Our goal now is to figure out the antiderivative of one of the pieces we've just created. Specifically, the integral of t2 points log t times 2 log t over t. To find the antiderivative of this part, we need a substitution that can simplify it. Let's consider the term t log t. This is an exponential function where both the base and the exponent are variables. A common way to handle these is to use logarithmic differentiation. Let's define a new variable, y, as t to the power of log t. This choice is strategic, as it directly involves the complicated term. Now, we'll take the natural logarithm of both sides of this equation to bring the exponent down. So, the natural log of y equals the natural log of t to the power of log t. Using the log power rule, we can move the exponent, log t, to the front. This gives us log y equals log t times log t. For convenience, we can write this as log y equals the quantity log t squared. Notice how taking the logarithm has transformed the complicated exponential expression into a much simpler polynomial in log t. Now, let's take the derivative of both sides with respect to t. On the left, the derivative of log y is 1 over y times dy slash dt. On the right, we apply the chain rule. The derivative of something squared is 2 times that something times the derivative of the inside. The derivative of log t is 1 over t. This result is critical. Rearrange this equation by multiplying both sides by y. We find that dy slash dt equals y times 2 log t over t. Now, remember that our original substitution was y equals t to the log t. Substituting this back for y gives us dy.dt equals t to the log t times 2 log t over t. This looks exactly like the integrand we're trying to integrate. This is the magic of this substitution. If dy-dt equals this expression, then the integral of that expression must simply be y. Therefore, the integral of t to the log t times 2 log t over t dt is equal to the integral of dy, which is just y. And since y is t to the log t, we found our antiderivative. The integral is t to the power of log t. We have successfully evaluated this complex part of the problem. We are now ready to apply the integration by parts formula to our integral I. Here is our split integral from before. Let's focus on the second integral. We will apply integration by parts to it. The formula for integration by parts is the integral of u dv equals uv minus the integral of v du. The formula for integration by parts is the integral of u dv equals uv minus the integral of v du. We need to choose our u and dv carefully. A good strategy is to choose a dv that is easy to integrate and a u whose derivative is simpler. A common choice is to let a polynomial or simple term be u. So, we'll let u equal t, the simple polynomial term. This means that the rest of the integrand must be dv. So, dv is t to the log t times the quantity 2 log t over t dt. Wait, is this a good choice? Let's check. To use the formula, we need to find du and v. The derivative of u with respect to t is 1, so du is simply dt. This is very simple, which is good. So du equals dt. Now for v. To find v, we need to integrate dv. And look, the expression for dv is exactly what we just found the antiderivative for in the last scene. The integral of dv, which is v, is the integral of t to the log t times 2 log t over t dt. And as we just learned, this is equal to t to the log t. This was the brilliant insight in this problem. We have all the pieces for integration by parts, u, dv, du, and v. Let's apply the formula. The integral we're evaluating is equal to u times v, evaluated from e to x, minus the integral of v times du. So that's t times t to the log t, evaluated from e to x, minus the integral from e to x of t to the log t, dt. Let's plug this result back into our expression for I. I is the first integral we split off, plus the result of our integration by parts. And now we see something wonderful. The integral of t to the log t from e to x appears with a positive sign and a negative sign. They cancel each other out. The two integrals cancel, leaving us with a much simpler expression. I equals t times t to the log t, evaluated from e to x. The substitution and integration by parts have completely eliminated the integrals. Evaluating this at the limits, we get x times x to the log x, minus e times e to the log e. Remember, the natural log of e is 1. So the second term becomes e times e to the power of 1, which is e squared. Finally, using exponent properties, x times x to the log x can be written as x to the power of 1 plus log x. So, our integral simplifies to x to the 1 plus log x minus e squared. We have successfully simplified the integral, I. Now that we have a simplified expression for our integral, we can substitute it back into the original equation to solve for x. Here is our original equation again. And here is our simplified integral, I. Let's substitute this back into the equation. The equation becomes e squared plus the quantity x to the 1 plus log x minus e squared equals x to the 4th. Notice what happens here. We have a plus e squared and a minus e squared on the left side of the equation. They cancel each other out. This gives us a much cleaner equation, x to the power of 1 plus log x equals x to the 4th. Now we just need to solve this equation for x. A key step is to use the exponent rule that says a to the power of m plus n equals a to the m times a to the n. Applying this rule, we can rewrite the left side as x to the first power times x to the log x. So we have x times x to the log x equals x to the 4th. We can now divide both sides by x to simplify further. Since we were given that x is greater than 0, we don't need to worry about dividing by 0. Dividing both sides by x gives us x to the log x equals x to the 3rd power. This equation has two possibilities. Either the bases are the same, or the exponents are the same, or both. This equation can be satisfied in two main ways. The first is if the bases are both 1. If x equals 1, then 1 to the log 1 is 1 to the 0, which is 1, and 1 to the 3rd power is 1. So x equals 1 is a valid solution. The second possibility is that the exponents are equal. That is, log x equals 3. To solve for x in this case, we need to convert the logarithmic equation to an exponential one. Since log refers to the natural logarithm with base e, log x equals 3 means x equals e cubed. Both of these solutions, x equals 1 and x equals e cubed, are greater than 0, so they are both valid solutions. Let's quickly recap what we did to solve this problem. First, we identified the key challenge, the integral. We isolated it and focused on simplifying it. Second, we used algebraic manipulation to break the integrand into two parts, which set us up perfectly for integration by parts. Third, we recognized a substitution opportunity within the second integral, which allowed us to find its exact antiderivative. Fourth, we applied integration by parts, and due to our clever setup, a cancellation occurred, simplifying the integral dramatically. Finally, we substituted the simplified integral back into the original equation and solved the resulting algebraic equation. Today, you've seen a beautiful example of how multiple integration techniques, algebraic splitting, U-substitution, and integration by parts, can work together to solve a complex equation. Thank you for watching.